This video presents an overview of a research project called Towards Stable and Diverse Generative Models with Dual Hybrid Quantum GAN. The goal of this work is to design a quantum-enhanced generative model that can produce realistic and diverse images while remaining stable to train on current noisy quantum hardware. Classical generative adversarial networks, or GANs, are very powerful for image generation, but they're known to be difficult to train. They can suffer from instability, exploding or vanishing gradients, and mode collapse, where the generator produces only a narrow set of samples instead of covering the full data distribution. Early quantum GANs, or QGANs, adapt this idea to quantum circuits. They can in principle represent complex probability distributions using superposition and entanglement. However, they face their own challenges: sensitivity to hardware noise, vanishing gradients in deeper circuits, limited qubit counts, and a strong dependence on qualitative, visual evaluation rather than standardized metrics. This project addresses these issues by combining hybrid quantum, classical generators with ensemble techniques, and rigorous, metric-driven evaluation. The experimental setup uses the Fashionist dataset, a common benchmark for generative modeling. Fashionist consists of 28 by 28 grayscale images of fashion items such as t-shirts, trousers, pullovers, shoes, and bags. The objective is to train a quantum-enhanced generative model that can produce synthetic images that look similar to fashionist examples while also covering the variety of classes and styles present in the dataset. This environment is simple enough to be tractable for current quantum hardware and simulators, but rich enough to highlight stability, diversity, and quality differences between models. The core contribution of this project is a dual hybrid quantum GAN architecture. Instead of relying on a single quantum generator, the system uses two independent hybrid quantum, classical generators that are trained separately but evaluated together. Each hybrid generator combines a parameterized quantum circuit with classical neural network layers. Both generators receive random latent vectors as input and output synthetic fashionist-like images. A classical convolutional neural network discriminator, similar to those used in DCGN models, receives both real images from the dataset and generated images from the two quantum generators, and learns to distinguish real from fake. During training, the generators try to fool the discriminator, while the discriminator tries to correctly classify real and generated samples. This adversarial process is implemented using a hybrid PyTorch and quantum computing framework, allowing gradients to flow through both classical and quantum parts of the model. To understand the design more clearly, consider a single hybrid generator. The process starts from a 64-dimensional latent vector, sampled from a simple Gaussian distribution. This vector captures random information that will be transformed into a synthetic image. First, a classical linear layer maps the latent vector into a form suitable for the quantum circuit. Next, this transformed vector is fed into a parameterized quantum circuit with 6 qubits and 4 entangling layers. Angle embedding is used to encode components of the vector as rotation angles on the qubits and strongly entangling layers built from rotation gates and controlled anode gates create rich correlations among the qubits. After the quantum circuit runs, the qubits are measured to produce a quantum feature vector. These quantum features are then passed to classical deconvolution and upsampling layers, which gradually reshape them into a 28 by 28 grayscale image. The combination of quantum expressivity and classical decoding allows the generator to model complex data distributions while keeping the quantum circuit depth compatible with noisy intermediate scale devices. The training pipeline alternates between updating the discriminator and the generators, following the standard GAN minimax objective. Batches of real fashionist images and generated images from each generator are fed into the discriminator, which learns to output high scores for real samples and low scores for fake samples. The generators are updated to minimize their adversarial loss, encouraging them to produce images that the discriminator cannot easily distinguish from real data. The entire process is implemented using a hybrid framework that integrates quantum circuit simulation and classical deep learning. Checkpointing and logging are used throughout training so that experiments can be repeated and compared under consistent conditions, which is especially important when working with quantum hardware or noisy simulators. Once both hybrid generators are trained, their outputs are combined using ensemble fusion strategies. The first strategy is pixel-wise averaging. Here, corresponding pixels from the two generated images are averaged, which tends to smooth out noise and make the outputs more stable. The second strategy is latent space mixing, where random binary masks are used to select patches from each generator's output and combine them into a single image. This encourages the ensemble to capture a richer mixture of patterns and styles learned by both generators. The third strategy is sample pooling. Instead of focusing on single fused images, the outputs from both generators are merged into one larger pool of synthetic samples for evaluation. By combining multiple generators, the ensemble can cover more modes of the data distribution and reduce the risk of mode collapse that often affects single generator GANs. To compare the single quantum generator and the dual hybrid quantum GAN ensemble, three widely used metrics are employed. Freshet inception distance, or FID, measures how close the generated images are to real images in a high-level feature space. Lower FID means better similarity. Jensen, Shannon divergence measures how similar the probability distributions of real and generated data are. Smaller values indicate better alignment and less mode collapse. Inception score estimates both the quality and diversity of generated images. Higher values are better. On the fashionist dataset, the dual hybrid quantum GAN ensemble achieves a clearly lower FID than a single QGAN, indicating that its samples are significantly closer to the real distribution. The Jensen-Shannon divergence also decreases, showing that the ensemble covers the data distribution more thoroughly and reduces collapse to a few modes. Inception score increases, reflecting that the generated images are more diverse and class-consistent. Similar patterns appear on NIST, confirming that ensemble strategies systematically improve fidelity, diversity, and stability compared to a single quantum generator. These results suggest several real-world applications for stable and diverse quantum generative models. In continuous biomanufacturing or other industrial processes, quantum generative models can help detect anomalies by modeling complex, high-dimensional sensor data and flagging unusual patterns. In fields like healthcare and finance, quantum GANs may be used to produce synthetic datasets that preserve important statistics while protecting privacy. Future work includes extending the dual hybrid quantum GAN to higher resolution datasets such as SAFAR10 or Celebe, exploring more advanced ensemble fusion schemes like weighted or adaptive combinations of generators, and incorporating noise-aware and error mitigation techniques for deployment on real quantum hardware. These directions aim to scale up quantum generative modeling while maintaining stability, diversity, and rigorous evaluation. In summary, the dual hybrid quantum GAN shows how multiple hybrid quantum generators, combined through ensemble fusion and evaluated with rigorous metrics, can deliver more stable and diverse generative performance on today's quantum devices. This work provides a practical stepping stone toward reliable quantum-enhanced generative mode.